to introduce our featured speaker for the evening.
Well, I'm really happy to introduce our speaker. Comes to us all the way from Illinois. I don't know if everybody knew, but he's selling his books here. Most of them have sold, but there's a few left. So if you're interested, which you will be after hearing his presentation, you can catch him right afterwards. I first met Theodore Gray at the Gem and Mineral Show that was held at Macomb Community College South Campus, where he was invited to give a very similar presentation. And I thought, boy, this would be enjoyable for us, even if it's not exactly astronomy, right? So that's why I made the connection in that short little presentation to astronomy. Our speaker is the co-founder of Wolfram Research, which, among other things, are the makers of mathematical software. He's the author of a number of books. One is called The Elements. There's also an app that he put out associated with that. It's been translated into 25 languages. His latest book is called How Things Work. There's a couple copies left of that. And his next project is going to be to do a book on machines. His title for tonight is The Periodic Table, a Work of the Ages.
Okay, hello. Everybody hear me? Perfect. Yeah. Working. Okay, good. So I hope that not too many of you were at that mineral show, because this is basically the same talk. So if you were there, you've heard it before, although there may be a few little variations. So is there sound coming from the computer?
Can be.
Oh, here we go. I think there is. Okay. So we're actually going to have that.
Oh, that's
Yes. We're going to have the song at the end, I think. So people can decide if they want to stay.
I was wondering if you were going to play that.
Well, maybe we could have a vote. Would you like to have the Elements song in English or in Japanese?
Both.
Japanese!
Good choice. Japanese is the correct answer. The second question is, do you want it now or do you want it at the end?
No.
One later? Okay. Yeah, let's do the English now, because it's shorter. And then, if there's appetite for it, we can have the Japanese.
Yeah.
So we can turn this up a bit.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercurium, and lindum, and magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, and plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendeleev, einsteinium, nobelium, and argon, kryptonium, and radium, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.
Embedded in this that you can see. The first one being 1959 when this was recorded, at which time almost the entire third from the bottom row had not yet been discovered. And the second date is the date in which this video was made, which was about 10 years ago, at which point the last 113 through 118 had not yet been named. So when you see the Japanese version at the end, it's longer because there were more elements discovered, and the video is a little bit more up to date. I should probably regenerate the videos with all of the currently named ones, but we'll get to that in a minute. Okay, so yeah, so there's, yes, this one now has everything, and we're finished. And people would please stop discovering new elements. Because, and actually, it's not that big a problem because we're not going to add a new row. I speak here for the publishers of periodic tables. We're not going to add a new row. If they discover 119, 120, 122, people are working on it. The same issue came up in the 1950s when Glenn Seaborg's work really, first of all, when it could be declassified. And he had to lobby periodic table publishers to convince them to add a row for all of his elements that he and his research group had discovered. And there was reluctance on their part because it's kind of a pain to have to add a new row. But he had filled in almost the entire row by the time he was there lobbying them to add it. And I'm very hopeful that we're never going to have enough elements to justify another row. So actually, I'm going to fix one thing here. Yes, okay. So actually, I gave this talk quite a few times last year because last year was the International Year of the Periodic Table, a UNESCO cultural year, on account of its being the 150th anniversary of the initial publication by Mendeleev. It also was basically the year, pretty much close to the year in which it was finished. So the last group being named. So it took 150 years to build this thing. From the first, serious conception that it could actually be possible to have a table like this to finally getting it done. Which, you think about things, okay, now I'm having problems. Why is it not going forward? This is like a completely different brand of computer. It's an IT. Okay, there we go. Okay, but I know why. It was because the menu was open. So anyway, so if you think about things that take 150 years to build, it immediately makes me think of cathedrals. And these were things where the architects knew they were going to be long dead by the time the thing was finished. I think it was less clear in the case of the periodic table. But after a few decades, I think people realized there was a lot of work to be done here. And people kept working on it, generation after generation, until, in our time, it was finished. So, of course, just like stone buildings go back much deeper in time than the great cathedrals, the foundations for this great work of ages were laid very far back. The alchemists, although they're criticized and made fun of, it was really the alchemists who started the quest for understanding elements. And the reason is because the alchemists had two goals in mind. One, impress the king so they could keep their job. The other was turn lead into gold so that they wouldn't need that job anymore. So this thing I've been showing you, this is lycopodium powder that was employed in the first job. It's great stuff. Known to the alchemists, known to the ancients. It's very impressive. It's my favorite powder. But while they were doing, party tricks like that, they were also hard at work, really trying to understand how might you go about turning lead into gold? Why does that seem to be so difficult? Because they've been working on it for hundreds of years and had made no progress. And they had learned to transform substances in all kinds of different ways, but they just couldn't get that to work. And why was that? So one thing they did was they developed this notion of a chemical cycle where they would take a substance, in this case copper, and say dissolve it in acid and then crystallize it into copper sulfate, which is blue. And they would go through a whole series of steps and come back and get the copper back out again. And so they studied these cycles to understand which substances is it that no matter what you do to them, you can always get them back out again. And copper is an example of that. And those things they classified as elements. Like, no matter what you do, you can't get rid of it. It's always still in there, even if it's a blue powder or a colored solution or whatever. So, you know, they did this sort of exhaustive analysis, and they decided that copper is an element, lead is an element, gold is an element, and no matter what we do, we can't get them to, you know, they don't mix. They knew that. They were not stupid. Like, they knew that lead and gold are different elements, and that no chemical process will transform one into the other. But they were stubborn, and they kept working on it. This is Hennig Brandt, one of the most famous of all the alchemists. His idea was to work with P, because it's yellow, it's a good start, you know, and it comes from living things, which, you know, living things were, you know, they're sort of magical. It was widely believed at the time, and up until actually fairly recent times, 1800s, that, you know, biochemistry, the chemistry of living things, was really in some fundamental way different from the chemistry of non-living things. So if you have a thing that comes from a living creature and it's yellow, he felt that was, you know, might have the sort of magical, super chemical powers that would be necessary. So he boiled tremendous amounts of it, hundreds of gallons, and discovered phosphorus in the process, a substance which spontaneously glows in the dark. It's a luminous substance, glows on contact with air. I mean, he must have been convinced that he was really onto something. It was the first new element discovered in millennia. The others were, you know, the only ones known at the time were known since antiquity. And it must have been a really magical day for him when out of all that pee came this thing with these incredible properties, and he'd have parties at night, people would paint it on their hands, and you know, it was a stunningly important discovery of its time. Whoa, the screen is going to mess something up if I touch that. And you know, phosphorus is now an extremely important element. It's a fundamental component of certain kinds of fertilizers. It's also how we burned his hometown to the ground in World War II with phosphorus incendiary bombs. We leveled Hamburg where he worked. So you know, it's like a lot of chemistry. It's kind of a double-edged thing. But you know, the alchemists were smart people. They worked very hard, but they never got that to work. So I'm going to do a little bit of history of the discovery of the element. So this is in 1669, the year in which Hennig Brandt discovered phosphorus. These were the things that were known to be elements. It's a little bit difficult to, you know, pin down what does it mean to discover an element at a time when the concept of an element was not completely well defined. But this is pretty much what was known. And these are things that, you know, things like gold, iron, whatever, these are things that have been known for a very long time. 200 years later, almost exactly 200 years later, in 1869, these were the elements that were known to Mendeleev just before he published his periodic table. So you can see there was a tremendous amount of work that had gone on in those 200 years. And that was the interval in which alchemy turned into chemistry. You know, of course, it was multi-generational. But this was the time in which, you know, the concept of being a scientist, the word scientist, the idea of applying for research grants from the king, you know, the importance of justifying your existence and systematically studying subjects, you know, that all came into being sort of over that same interval of time. And, you know, and a great many things were discovered. So I'm showing the elements here in the way that they were arranged, that they are arranged today in the modern periodic table. But at the time, in 1869, it was just a stamp collection. There's like this, here's all these elements. We know they're elements, we know you can't transform one into the other, you can't create or destroy them, but there was no logical order to them. They were just, people would list them alphabetically or something, because they didn't have any better way of organizing them. But they were tantalizing hints. I'm going to mute that. hints that there must be some sort of logical structure to it. So, for example, integer ratios between the reactants in gas reactions. So if you react hydrogen with oxygen, both of which were known, you combine volumes, a certain volume of oxygen, a certain volume of hydrogen, you will find that it's always 2-to-1 ratio, at which all of both of them react. Always twice as much hydrogen to the equal amount of oxygen, to a certain amount of oxygen. How can that be? Like, why would chemicals behave that way? And if you think about it, there's really only one logical answer, which is that there are tiny, tiny particles, too small to see, and those particles are combining in integer quantities, like 1 oxygen and 2 hydrogens go together to make water, because it was known that you react these two, you get water, and that the ratios are equal, or 2-to-1 like that. And there were many such ratios discovered, and through various clever ways. And actually, so I gave this talk in Palermo, and fortunately, just before I gave the talk, somebody pointed out to me that one of the Stanislaw Cannizzaro, a name that I vaguely remembered but hadn't really remembered what he did, he actually showed how it was possible to use these gas ratios to figure out molecular weights. At first, just ratios of molecular weights, and then how to relate them to the molecular weights of things that were not gases. So it was a complicated sort of self-referential thing, but eventually it became possible to figure out what the mass of these tiny particles that we couldn't see, what those masses were. More specifically, the ratio of the mass of the particles in one element to the ratio to the mass of hydrogen. As a footnote, it was not known that hydrogen is diatomic, that hydrogen gas is actually H2. Didn't know that. So for quite a long time, all the atomic weights were off by a factor of 2. But it doesn't matter, because it's really only the ratios that matter. And then people started to notice patterns in the chemical properties of groups of 3 elements. They called them triads, where there would be 3 elements in a row whose molecular weights were approximately equally spaced, that shared similar chemical properties. And this was all very mysterious. It seemed like, there's got to be something going on here. Why do we find many sets of 3 elements, equally spaced molecular weights, and they seem to be kind of similar to each other? It was actually sort of a popular crackpot hobby at the time to claim that you had discovered the secrets of the universe, that you saw the pattern in all of these relationships. And you can imagine the amount of nonsense that was written about these triads and their relationship to the orbits of the planets, and harmonics in music, and just all kinds of, people are very good at seeing patterns where there are no patterns, and making up, connections to things that coincidentally seem to be related. So there's this guy who was one of those crackpots, and he made up all these wild theories about how everything fits together. The beard really didn't help; it was not widely believed. Most people thought he was nuts, and he was from Siberia. And I just look at the beard, But that was Dmitri Mendeleev, and he was right. He actually got it right. So another thing that didn't help him was that he wrote up this table, and there were problems with it. For example, the molecular weight, or the atomic weight of tellurium and iodine. He said, you're just wrong. The iodine is heavier than tellurium. It just has to be, because look at my table. It's so obvious, it has to be. And the fact that you're the president of the Royal Chemical Society and known as a careful experimenter, and you have very carefully determined these measurements, you're just wrong. I mean, he completely dismissed the experimental evidence of some of the most respected scientists at the time and told them that they're wrong because his table must be right. He really was not believed for quite a while. But what he did that others had not been willing to do is he made absolutely firm predictions. He said, in my table there is a hole here, germanium for example, I didn't have a name at the time. There's an element that will go here. He predicted 4 elements. You will find an element, it will have approximately this molecular weight, it will have these chemical properties. And if you don't find it, I'm wrong. And I will, apologize and go back to Siberia. He staked his reputation on it, which is, of course, that's sort of pretty much fundamental to the scientific process. If you've got a theory and it's right, it needs to make predictions, and you need to be willing to accept that if your predictions are wrong, then your theory is wrong. And as those, it took about 20 years before all 4 of them were discovered, but all 4 of those elements were discovered in exactly the place he said they would be, with exactly the properties he said they would have. And, it became hard to deny that notwithstanding the beard, he was right. There were others who proposed very similar tables at roughly the same time, as is usually the case in these sort of things. It was in the air. But I think it's sort of fair to give him the credit for it, because he's the one who was most right about most things, and he was the bravest in making these predictions and not beating around the bush. So that's why we give him the credit. So here's a little video. This is the order of discovery of the elements. So as each year goes by, you see not much is happening right now, but we're about to get to Hennig Grant, and Phosphorus will pop in. There you go. And now you see I've slowed down the rate now by quite a bit, because this is the point at which things really get going in science and chemistry. And these things start popping in. And actually from here on out, it's a pretty steady pace, right up to 2016, I guess. Pretty steady pace of discovery. There's different fashions. The sort of basic workhorse elements were filled in first. There was there's a whole bunch of rare earths just appeared down there, all from the same mine in Sweden. And then, so now we're getting into the nuclear age. So you're going to start seeing the Mr. Glenn Seaborg's elements being filled in there, and then now we're up to the 90s. So now it's those last few stragglers that filled in. But it's a surprisingly steady rate over the last 200 years or so, or just about 300 years, mid 1700s. That these things were discovered one after another. And it really, it sort of makes you appreciate the sense in which this is a multi-generational project that was, it was built up by many, many people. Each of them, once Mendeleev had published the table, everyone knew what the playing field was. It became quite competitive, because if you discover an element, you get to name it. And particularly towards the end, there were epic battles, not about the discoveries, that's actually fairly maintained and of very little interest really once you get to the last dozen or so. But the names were the subject of great controversy. Glenn Seaborg, for example, his Seaborgium was named after him before he was dead, which at the time was just not done. And the group in Russia, the Dubna group, did a horse trade with the Berkeley group and said, okay, fine, we will let you name, we will not contest the naming of Seaborgium, but you have to let us name Dubnium, which Berkeley claimed to have discovered first. Berkeley group agreed to give Russia the name in exchange for honoring their great Glenn Seaborg before he was dead, and the deal was made, and I'm told that people in Berkeley still will not call Dubnium Dubnium, because in their hearts they know they got there first. But anyway, the re-arguments really are entirely about the names. And Oganesson was then named after a living Russian at the end, just to complete the horse trade there. Anyway, so brief history of the periodic table. So, so I compared it to the construction of cathedrals, but just as in the case of cathedrals, there are setbacks in the construction. There were a number of them. In the construction of the periodic table. The first one being, and one of the most serious, was this tellurium iodine problem. That, the molecular weight of tellurium and iodine appeared to be in the wrong order. It's like the molecular weights, if you go through the periodic table in the obvious rows and columns arrangement, the measurements were not wrong. It's the atomic weights are wrong. The atomic weights are wrong. And remember, I've been saying atomic weight this whole time, not atomic number, because at the time that the periodic table was constructed, it was not known that there were protons and neutrons and electrons and things in orbit, and the notion of atomic number didn't exist. There was only atomic weight. And as it happens, fortunately, or people might never figure this out, atomic weight goes up pretty much uniformly with atomic number. Each higher atomic number is also a little bit heavier, except iodine and tellurium. For completely uninteresting and random reasons, naturally occurring iodine and tellurium happen to have an anomalous number of neutrons such that it crosses over. And the careful measurements of the day were not wrong, and Dmitri Mendeleev was not wrong. Both people were right, but there was absolutely no conceptual framework at the time for anyone to explain this. And so everyone just decided to sweep it under the rug and ignore the issue. They just literally said, we don't understand this, but we're just going to go with it anyway, because the table seemed so obviously correct. And it wasn't until 1913 that the discovery of isotopes and the idea that there could be atoms of the same element that have different molecular weights, and that there were these, basically the whole atomic theory of the atom worked out, and this notion of neutrons, and there aren't really, there aren't just 100 elements, there's actually thousands. There's something like 3,100 different isotopes that have now been measured and characterized. That was the explanation, but it took a long time, and people just sort of ignored it. Another problem is radioactive decay, because basically it turns out that elements, basically the two fundamental principles on which the periodic table was based, which is that all atoms of a given element are identical, and you can't transmute elements one into the other. Both are wrong, and yet the periodic table survived, though both of its foundational principles, in fact, being, when you get right down to it, false. There are different isotopes of the same element, yet they're the same element. And you can transmute, you can turn lead into gold. It's perfectly possible. It can be done, no problem. The alchemists were right. They just, their job title didn't survive long enough to arrive at the invention of nuclear reactors that you need in order to do that. And it turns out it's more expensive than digging it out of the ground, so people won't actually do it. But basically, you can do it. And the periodic table remains useful because we now understand at a deeper level where it comes from, and what does it really mean for something to be an element. And the fact that you can transmute them is okay because you do it nuclear chemistry rather than regular chemistry. So another sort of issue that's come up in the history of the periodic table is how to draw it. And there's a great many, different shapes that the periodic table has been drawn in. The Mendeleev's original version actually was sort of a transposed version, where rows and columns are interchanged. There are versions of it where the transition metals are interleaved with the rightmost columns, and that's published that way often in Russia to this day, because it brings together certain other kinds of properties that are more convenient. People make spirals. Every once in a while you'll read in the newspaper that somebody has published this new arrangement of the periodic table, and now suddenly school children will be able to understand everything because this is, the spiral galaxy version of the periodic table will make it all very clear. Personally, I think this is all nonsense. They all have compromises, all these different possible arrangements. You can criticize in one reason or another, including the standard arrangement. This one is full of compromises too. But it's fine. And, when you get right down to it, what I think is much more interesting to talk about, rather than the sort of layout or structure or whatever of the periodic table is the elements themselves. That's what originally got me interested in you know, working on this subject in the first place. It wasn't, you know, it wasn't anything globally about the periodic table. It was, there's a lot of really cool stuff in there. Each of these things individually is a wonderfully interesting thing. So, you know, in a sense, it's like, actually I wrote an article for some science, you know, some journal about, they were doing a special issue on the periodic table, and I compared it to, people complain that, okay, so mathematics is pure science, and math and logic is pure. You go to one step to, you know, one step into the realm of practical, you get physics. And after that, it's all stamp collecting. You know, chemistry is just a whole bunch of arbitrary, random sort of different substances, and there's nothing really fundamental to it. But I think that's actually, I think a better analogy is something like the rules of chess. You know, we have these things, they exist, and let's look at what we can do with them, and the ways in which they can be combined, you know, following the rules of quantum mechanics to determine how these things react with each other. It's really astonishing how much variety is possible within, you know, this is the catalog, this is what you got to work with, what can you do with it? Well, for example, you know, people, that's one thing you can do with it, or the entire universe that we know. So anyway, yeah, so I now have a collection of stories about elements, individual elements, one at a time. And I could go on forever with those stories, so you just tell me when to stop and we can have questions. I don't actually know how long I'm supposed to talk to, so I'll start with my first one, which is rust. I mean iron. Iron is great. It's, iron is an amazing substance. There's huge amounts of it. It's incredibly cheap. There's just tremendous quantities of the ore readily available in quite, you know, concentrated form. It's by far the most flexible material to build things out of. You can cast it, you can machine it, you can weld it very easily. It's quite easy to extract from its ore. You can alloy it in an astonishing, you know, range of ways to produce anything from, you know, a soft, you know, mild steel to a very hard but brittle cast iron, or, you know, this incredibly hard high-speed steel, tool steel alloys. You know, basically everything that you'd want a metal to be is iron, except it rusts. Like, and that didn't have to be. There's no particular reason why there's a relationship between all these desirable properties of iron and this roughly $1 trillion a year of economic harm property of it, the fact that it rusts. That's just bad luck, you know, chemistry speaking. And so, you know, I find iron to be a very, you know, in a sense, inspiring and depressing element, because you have all these beautiful things and they're constantly rusting away. It's a metaphor for getting old or something. But what can you do about it? Well, not much, but you can at least make it more attractive. So for example, high-speed rusting, if you just, and this is the thing anybody can do, I did this when I was a kid and annoyed my mom, if you have fine steel wool, the 040 steel wool, just light it with a match, and it burns. It's amazing. I understand they teach Boy Scouts to start fires that way with a 9-volt battery and some steel wool. And it's not technically exactly the same reaction, but it's oxidation of iron, and you get iron oxide out. Close enough, I call it high-speed rusting. Another thing you can do is reverse rusting. If you have something that's already rusted, you have iron oxide powder, you can actually unrust that back into iron metal. So this is what's called the thermite reaction. And what you do is you have iron with oxygens attached to it, and you find something that likes those oxygen atoms even more than the iron does, that thing being aluminum. So if you mix iron oxide powder with finely powdered aluminum and light them, I think he used a acetylene torch, but you can light it with just a fireworks sparkler. The aluminum will grab the oxygen, rip them off the iron atoms, And the result is aluminum oxide, corundum, and iron, pure iron. But not just any old iron, white hot liquid iron, because it turns out the aluminum really likes those oxygen atoms. It releases a tremendous amount of heat. So what you get is liquid iron. And the video you just saw, that is thermite welding. It is the way in which high-speed train tracks are connected to each other. You imagine you have two train tracks, two sections of train track, and it's a 100-foot long section of iron, and it's 3 inches thick. Even the webbing is 1.5 inches thick, and you need to butt weld these things together in a way that you can't just go around the outside. You can't just bevel it in and do some little welding like that. There's going to be trains going over this for 50 years, hammering on it. You have to fuse these things together so that as if it's one piece of iron. It's actually very difficult to get enough heat in fast enough, because of course you've got these 100-foot long sections of iron trying to conduct the heat away. It can be done with very, very large electric arc welders. When they're building, long sections of high-speed train track, they will bring in huge pieces of equipment that can actually do this electrically. But what if you need to fix, make a repair? The answer is thermite welding. So you just build a mold around the section of train track. You put about 10 pounds mixture of iron oxide and aluminum. You light it and walk away. In the bottom of the canister, there's a disc of aluminum, solid aluminum metal disc at the bottom. As the reaction proceeds down, it gets hotter and hotter. When it reaches the bottom at just the right point, the aluminum plug melts through, and the iron pours down, fills up the mold. It completely melts the both ends of the track, fuses it into a single piece, and I think somewhere in that video there they show a cross-section cut away. It basically becomes one piece of metal. It's also a beautiful classroom demonstration. You do it in a flower pot, and you get a tremendous amount of heat. And it restores, it undoes the damage of rusting, get back the iron. But you have to use aluminum powder, which is, chemically speaking, much harder to get than iron. Another example of the power of moving oxygens around. So you've probably all seen the demonstration of lighting magnesium ribbon. Right? You light a magnesium ribbon, it burns very, very brightly. It's getting oxygen from the air, it's burning, it's nice. But what if you were to put that into a block of dry ice? So that demonstration is some coiled up magnesium ribbon packed into a hole in a block of dry ice. Now, dry ice is used as a fire extinguisher, for example, and particularly in the restaurant industry. It doesn't contaminate food, it's very convenient as a fire extinguisher. But it greatly accelerates the combustion of magnesium, because it turns out that magnesium likes oxygen better than does carbon. And so if you have magnesium burning in the presence of CO2, dry ice, it will seal the oxygens off. And because it's a solid block of CO2, the concentration of oxygen is actually much higher than it is in the air. So despite the fact that it's very cold, you get a much more vigorous reaction. And I carved ear holes so that it would look, I don't know, it's like an angry boss kind of blowing steam, whatever. That was done for artistic effect. But it's a nice demonstration of a couple of things. One is oxygen. It's good to have if you want fire. It's a demonstration of why metal fires are hard to fight. Because if you have metal on fire, almost anything you do is going to make it worse. Throw water on it, that's a terrible idea. You hydrolyze the water, create hydrogen gas, and the whole building blows up. You try to throw CO2 on it, it just makes it worse. So for a while, the sort of official recommendation was dry sand. If you have, let's say, a sodium fire, a magnesium fire in an industrial setting, you would shovel dry sand onto it. And that works unless somebody has recently washed the floor and your sand isn't dry. And then when you shovel the sand on, you die. And there were several people killed in a disaster at a sodium processing plant. This was now maybe 20 years ago. As a result of which, the recommendation now pretty much is just leave. Go away, because basically nothing you can do is going to help if you have a significant quantity of metal on fire.
Sand will save you this time.
Hmm?
Sand will save you this time.
Yes, sand will not save you. Well, it would if it was dry, but the question is, how sure are you that your sand is dry? You know, do you stake your life on the sand really being dry, or would you rather just leave and let it burn out? Because it will burn itself out. We had so I live in Illinois, and there was an absolutely spectacular magnesium fire in Indianapolis, which is only about a 2-hour drive, and I went to see it because it burned for 3 days. And it was a magnesium recycling plant. They had thousands of pounds of magnesium bars, and it caught fire, and they evacuated a neighborhood. You know, hundreds of homes were evacuated. The thing burned for 3 days, and nobody died because they didn't try to put it out. It just, if you can imagine the brightness of thousands of pounds of magnesium burning, it was amazing. Also, you know, caused hundreds of people to be evacuated and destroyed the facility. But
Question?
yep.
Could you have extinguished it with nitrogen or obviously argon?
Yeah, inert gas. Nitrogen probably, although a hot enough fire will split nitrogen. But I don't think you can form any compounds, so that probably would work. But with a gas like that, the question is, how do you get it, you know, how do you keep it concentrated in the building enough to actually put it out? And the stuff will stay hot, you know, above its ignition temperature for a long time, so as soon as the gaseous agent dissipates and air comes back in, chances are it will relight. So, you know, it's just, basically people don't try for the most part. And, you know, first of all, make sure that you don't have that fire in the first place. And then don't worry too much about putting it out. Or, you know, in an ideal world, you design a facility to be able to withstand that sort of event. You know, kind of like the DuPont gunpowder rolling mills, where they built 3 walls out of 2-foot thick stone, 4th wall out facing the river out of wood, and every once in a while the thing blows up, and that's fine because the wood goes out into the river and they rebuild the wall and start over again. Nothing else, you know, is harmed. That's a tangent there. Anyway, so another example of oxygen. So this is it's a bacon lance. I call it a bacon lance. So it's a steel cutting tool made out of bacon. Actually, prosciutto. Okay, it's prosciutto. I admit it is prosciutto because bacon itself falls apart. But what the gas is flowing through is oxygen. So you know, it's a demonstration of the fact that in a lot of you know, cases where we talk about a powerful fuel, really what's more important than the fuel is the oxygen. So, for example, the Saturn V moon rocket's the most powerful engine ever made. Do you know does anybody know what the fuel was in the Saturn V? Well, oxygen plus what? Kerosene, yes, kerosene. Basically diesel fuel. I mean, it's essentially the same thing that trucks burn on. But it was burning that kerosene in combination with liquid oxygen. And, you know, that's the difference between taking your Amazon shipment across the country and going to the moon. Not the fuel, it's the oxygen. And similarly here, the difference between lunch and melting through steel is the concentration of the oxygen that it's burning. This is actually based on a real device called a thermic lance, where in place of bacon they use a mixture of iron and magnesium rods inside an iron pipe, blow pure oxygen through it, and you get a tremendous amount of heat coming in. You can cut through concrete, melt through concrete with the heat coming out of the iron, the reaction of iron and oxygen. So this is hydrogen plus oxygen. If you blow soap bubbles full of hydrogen and oxygen, you get fire. But what kind of fire depends on the ratio, like we were talking about at the beginning with these strange integer ratios. So if you have just, let's see, which one is this? Boom, okay. Yeah, the very first one, hopefully you saw it, it's kind of like a jellyfish. It's quite quiet almost, sort of a whoosh sound, because the hydrogen is mixing with oxygen from the air. But if you mix in enough oxygen so you have nice, you know, close to the ratio, the 2-to-1 ratio that you need, you then get something more like a gunshot going off because the reaction is much faster. It's a common classroom demonstration for more adventurous chemistry teachers to show how as the ratio approaches 2 to 1, you get more and more vigorous reactions to the point where it's knocking the chalk off the chalkboards. So I spent a long time writing a column for Popular Science where I would do each month some new topic in chemistry. And I learned a lot doing that, one of them being that you have to really think about why should somebody care about this. So for example, for a long time, too fast, right? So I spent about a year trying to convince my editor there to let me write about the hydrogen soap bubbles because I thought they were so cool. And I thought, obviously people will be interested in this, cool, chemical demonstration of stoichiometry and such. And it did not go over well with him. And he said, well, I don't care. And why should anybody else care? And it took me a year to figure out why this actually helps you understand something about the world. And the answer is, if you live in the Midwest, I'm not sure about here, like in rural areas here, probably the same. But if you live around where I do, if you're not inside the city and you're out in the country, your source of heat in the winter is propane. And a big truck comes and fills up your 500-gallon propane tank. And like on the East Coast, it's heating oil, but around where I live, it's propane. Every once in a while, like once a year roughly, you'll read the exact same newspaper article, which is so-and-so came home from vacation and discovered that their roof was in their basement and their walls were out in the cornfields. It's always cornfields because that's the only thing we grow. And it's never in town, and it never happens when anybody's home, very rarely. These things do happen sometimes and people are killed, but almost always it happens when somebody's on vacation. And the answer is that there was a propane leak. And it filled up the basement or the crawl space or whatever with propane, which is viscous for a gas and heavier than air. And it filled up until it reached a pilot light somewhere, and then detonated like a bomb. And the roof goes and then falls into the basement, and the walls go out in the cornfield. And so the question is, why does the same gas burn, gently and safely in your grill or in your hot water heater or your furnace, gentle blue flame, everything's fine, or blows your house up? And it's that's what the bubbles demonstrate. If you pre-mix the gas with an oxidizer, the fuel with the oxidizer, you will get a much higher rate of reaction. So when you're burning propane in a stove, it's burning slowly, not because the reaction is slow, but because you're metering the reaction by how you're releasing the gas and allowing it to mix with the oxygen from the air, so you get a gentle flame. If you release the gas first, let it mix up with air, and then light it, you will get a tremendous explosion. Same chemical, same fuel, same oxygen, different rate of reaction due to mixing. And that's sort of what convinced him that this was sufficiently interesting to let me write a column about it. And that was like, each month I had to figure out how does this explain something to somebody in the real world. Same thing explains the fuel air bombs, etc. So like I said, I can keep going.
We've got about 10
But
minutes.
yeah, so maybe this is a good time for
you want to
questions.
Kick it over to questions, yeah.
Sure. Yep.
Want to bring up the lights?
I'll just flip through these screens while we're waiting. This is lithium burning. Okay, I'm just going to tell you about lithium, okay, because I'm so proud of this. So, I'm going to assume that you all know about alkali metal explosions. For example, throwing sodium in a lake. It's a great idea. Everyone should do it. It blows up. Lithium, if you've ever seen the chemical, science demonstration of dropping lithium in water, it usually sort of bubbles a little bit. You get hydrogen, it reacts with water and releases hydrogen, but it never gets hot enough to actually explode. We were filming this for a NOVA show, and I got my lithium by unraveling a AA single-use, disposable lithium cell. It turns out they do something to the lithium. They activate the surface somehow. So it actually caught fire. And what you're about to see is the holy grail of alkali metal water reactions. The thing that I'm always trying to accomplish and have only ever done before with sodium and higher, which is, wait for it, wait for it. Any second now? Oh, is this the wrong one? That was that one. Oh, never mind. I have to go to the next slide. Right, here we go. This is the one. I'm approaching this now.
You've got our attention.
Okay. This is slow motion. It's like 10x slowed down, so that's why you have to wait. Yeah, if you can break the container that it's in, that's sort of a very good visual demonstration of the force of the reactions. Of course, as soon as that happened, we got every glass thing we could find and broke all of them. And that was probably like the, I don't know, the fifth one or something. It was not the first one. Just to get the perfect breaking glass explosion. And doing that with lithium as opposed to sodium, and you can do it with sodium any day. That's the sodium party I had. But doing it with lithium, I'm very proud of that. But anyway, we'll go to questions now.
Let's thank our speaker.
Japanese element song, absolutely.
Yes, we can.
We'll skip ahead. Okay, just really briefly. Okay, this is if you want some fresh salt, you know that stale store-bought salt. You want fresh salt. So we are blowing chlorine gas into a pool of molten sodium, and the smoke coming off, of course, is sodium chloride, table salt, and we're salting popcorn with it. So what I didn't think about is the fact that that net is made of plastic. So you notice I reached for the chlorine cylinder first, because that would kill us all. That's a substantial amount of chlorine. So that was what you call a flaming disaster. However, first of all, we got the shot. You know, that was what was in the magazine. It was beautiful. And then, by pure luck, we got what I think is the most beautiful picture that I've ever been responsible for. There's actually a different photographer who pushed the button, but this one. I mean, it's like, you have to see this in high res, in a dark room. It's just beautiful. You have the fire, you have the little spiraling, at the end of each of the little smoke trails is a glowing ball of flaming liquid sodium shooting out in all directions. And it was glorious, and that's in the Mad Science book that there are no copies left of. Anyway, okay, now I'll stop and we'll
I used to have fun blowing things up too. Ken?
I've got a question for you. One of the things I noticed on that chart of how the elements were being discovered and such, I noticed that helium took until 1900 to be discovered.
Yeah, and helium was named after the fact that it was discovered in the sun first, before it was discovered on Earth.
Okay.
Because the problem with helium is that, you know, first of all, actually, if you look, the entire right-hand column came very late.
Yes.
The noble gases, because
Neon too, right.
you know, because they don't react with anything. You know, they are chemically inert.
But we were using neon before 1902, weren't we, or not?
Yeah, I'd have to look at the video to see, but I mean that column was quite late on the whole.
Okay.
And you know, helium in particular, it's very light. If any that's released into the atmosphere goes up and is lost to space.
Right.
There's not a lot of it around. You know, it's hard to find.
Okay.
And it was named after the sun because it was first identified as a spectral line in the solar radiation that was not explainable by any known element.
It's remarkable though that it was so late.
Yeah, no, it is.
Other questions? Way in the back.
So what happened with the periodic table that discovered the island of stability?
Okay, so I hate that name because it's not going. There are not going to be any stable elements. People talk about this island of stability around 122.
It'll maybe last half seconds.
Yeah, maybe milliseconds instead of nanoseconds. And you know, I don't know. I have a bad attitude about the elements past about 100 because none of them have any practical applications And the only reason, and no interesting science has been done in their discovery or through the study of their properties. It's a pure ego game to get to name it. I really believe that. Like there's just not much of interest in the discovery of those elements other than filling in the periodic table and then getting, your institute or your state or your country or yourself in the name of the element. Because if you think about it, it is the most exclusive club, really. Like there's just not a lot of things where there's a table written down and this is it. And it's filled in now, there's none left. People got frantic towards the end because there were only, half a dozen slots left and 3 laboratories working for them. But anyway, I don't know. I guess other people can be interested in those elements. I find them just irritating.
Yes.
So are you saying?
Louder.
So are you saying we're not going to discover vibranium?
No, I think that it probably will be discovered, but it won't be stable. It will have a slightly longer half-life than its neighbors.
Oh, so we can make Captain America's shield, but it only lasts for half a second.
Yeah, if that. Plus, it wouldn't work anyway. I mean, 113 was discovered, it was confirmed on the basis of 3 atoms of it, having been verified as being made. That's the standard of discovery. It's not like they have a lump of it.
Oh.
Other questions? Yes.
Yeah, I'm wondering about the powder coating that surrounds an arc welding rod. And I'm wondering, what is it composed of? How does it work?
I don't know. I would guess it's a flux of some sort, but I'm
I think
not
it's
that.
inert gas in a solid state.
Did
I
it?
think
Probably.
that's what it is.
I mean, it could well be something which is designed to, like a flux. It's designed to vaporize and release perhaps nitrogen. I'm not sure. Yeah, I'm sorry, I don't know the answer to that.
We're running out of time, and I think a lot of us would like to hear that song in
Okay.
Japanese.
Okay, so I'll give you the very brief preamble. So, we're in 2010, simultaneously with the release of the iPad, we released an iPad app version of this Elements book that I have here. And for some reason, it did really well in Japan. It was selling a lot of copies in Japan. We had a translation into Japanese because the print book had been translated into Japanese. And I thought, I should make a version of the app, and I should do something special for the Japanese market because it's so popular there for some reason. And I thought, wait a minute. I remember I have a cousin that I had forgotten about for decades, but I remembered I have a cousin who was he didn't succeed being a rock star in America, but he's very handsome, and he moved, and a good musician, so he moved to Japan, and he's like a pretend American rock star who plays in hotel bars in Osaka. He plays piano, he sings covers of American popular songs, he records music for Japanese video games like Dance Dance Revolution, that kind of thing. So he makes a living as a musician in Japan. And he has 2 twin daughters who would be there, my first cousins once removed, who also sing. And I thought, I will make a J-pop, sickly sweet, almost unbearable version of the Elements song and record it. I'll have him, arrange the music. And we'll put that in the Japanese version of the app. And this is the result. So these are my first cousins once removed.
「
Well, our speaker has a few books left for sale. Where are we going next?
Red Coat Tavern. Yep, north of Watering Hole, just north of 13 Mile on Woodward.
Astronomy after astronomy.
That's right.
Good night.
Good night, everybody.
Very cool. Good team, son. Enjoying yourself there?
Thank you so much. It's not perfect, but it sure works out a lot better than right here. Very good. Bill?
All right, I see you brought the gas tonight. And then Daddy's right. That's the plan.
You have the answer?
Yeah.